Network DNS of service protection. So in a peer-to-peer network, you receive a lot of data, right? And you can connect to any peer, as we looked at before, and this is quite, I would say, it's a hostile environment because anyone can connect to you and send you some data, and then you're gonna have to process it. And that's why there are some simple sanity checks here that are being done when you receive some data. And these sanity checks are typically low cost for you, so you can perform them quickly on a lot of data. So you check, is this transaction bigger than it should be? You check whether the transaction used the correct encoding. And once you're kind of comfortable with the contents of the transaction on the block that you received, then you can go on to make a signature validation of the transactions. So this is the most CPU intensive operation when you receive data on the network layer. And that's why this is typically done at the very end of the validation of a transaction. And if the signature is wrong, then Bitcoin associates a penalty of 100 points to an IP address, right? And this means it will then disconnect for 24 hours. So it will kind of go into a blacklist. The same goes if you receive a transaction that spends twice, basically, that spends a UTXO that was already spent before. So that's a double spending transaction, which you don't want to forward. So whenever here there's a malicious transaction that gets sent from A to B, then the connection here gets discarded and you get a 24-hour ban. That's the DOS protection mechanism in Bitcoin. So how can you exploit such a DOS protection mechanism? So think of this picture here that you see, pause the video for a minute and think of what could you do to exploit this mechanism. How can an adversary take advantage of the DOS protection mechanism? Okay, so what an adversary could do, so here this is the adversary, that's the bad guy. He's sending a transaction to Tor. So this transaction, for example, has a bad signature, right? So if you have a Bitcoin connection to one of these peers or to all of these peers, and you're sending this transaction to all of these peers, then these peers, they will suddenly associate a penalty. They will associate a penalty of 100 here to you, right? And once you have this penalty, you're banned for 24 hours, right? You're basically, like this Tor exit node here cannot connect to this peer for 24 hours. Now, let's say there's some nice guy coming, right, like you, and you want to establish a TCP connection here through Tor because you like to be anonymous with your Bitcoin client, and you're trying to reach out to this guy. He will say, no, I'm sorry, you're currently banned for 24 hours because UIP of this is the exit node of Tor, sent some malicious data. Right? So just to give you some background knowledge about Tor. So Tor is the onion router. It's basically you have a network of peers that you can use to send data. So let's say this is here you, or one second. Let's say this is your target, and this is you. Then you can send a transaction through the Tor network, and your IP address to the recipient will look like the IP address of this very last hop, right? So you have kind of here like a multi-hop layer. This is the exit, right? And that's the ingress node. So you're only aware of this guy. You can check which exit node you're using, and you know which target you want to send the transaction to. But now if all the exit nodes, right, all these exit nodes here were used to send malicious data to other peers in the network, then those connections will be dropped and nobody can use Tor anymore through Bitcoin, which is bad, because many people like privacy, and privacy is a fundamental human right. So that's a process whereby all Tor exit nodes can be banned through Bitcoin.